So I'm going to talk about, just quick summary of what I'm going to talk about. I've got a compact symplectic manifold. D in X a divisor. Then the question is how to understand the Fukaya category of this compact manifold from the Fukaya category of the complement of the divisor. This is a strategy for understanding Fukaya categories that goes back to Paul Seidel. But I'm going to start by giving the main example and application of the ideas and the results I'll talk about. And that's a new proof of homological mirror symmetry for green-Plesser mirror pairs. So let me summarize for you, or let me state the theorem for you. Input data is a lattice with a reflexive polytope. We've got normal fan, which I'm going to denote sigma bar. The one-dimensional rays are generated by vertices of the polar dual reflexive polytope, delta naught. We're going to choose a simplicial refinement of sigma bar whose one-dimensional rays are the set of lattice points in the boundary of delta which are not in the interior of a codimension 1 face. Okay. These refinements always exist. Now, so I think I want to have a split board for the next part. So from our fan sigma, we get a toric variety which we'll call Y. And a line bundle L. S is going to be a section of this line bundle. X is going to be the hypersurface it cuts out. And we're going to have a divisor in X, which is its intersection with the toric boundary divisor, which I'll denote by del Y. And we can break this up into components dp, indexed by this set. I've forgotten how you say this letter. Whatever it is, psi. Psi, is it? Okay, thank you. I don't even remember how to LaTeX it. I don't know how that happened. Okay.
You're not a contact
Obviously. So here we have a manifold X. We're going to assume it's smooth and some divisor inside it. So that's the side we're going to look at the Fukaya category on. This is the toric boundary divisor.
That's toric divisor.
Toric divisor, yes. So this has components indexed by the one-dimensional rays of the fan, which are exactly indexed by psi. So that's why when we intersect it with X, we also get a bunch of components indexed by psi. Okay. On the other side of mirror symmetry, we're going to take the polar dual polytope, delta circle, its normal fan, sigma bar circle, and that's going to give us a toric variety Y bar circle and a line bundle L bar circle. And we're going to look at a family of hypersurfaces in this toric variety parameterized by affine space with coordinates indexed by psi. So how do we define this affine family? Our line bundle has a basis indexed by the lattice points inside delta naught. And we define, maybe I'll put this down here. We look at the family of hypersurfaces cut out by an equation that looks like this, where these chi are the corresponding sections of this line bundle. Okay. Oh. Right. So we're going to assume X is smooth. And we're going to assume omega is the restriction of some toric Kähler form from the ambient toric variety. that means the cohomology class of this scalar form is going to be some combination of the Poincare duals to the components of this divisor. Sorry? They will be, yes. That's right, I'm going to assume that they're positive. All right. Now here's the main theorem. Sorry, is this invisible shield? No, okay. Suppose delta is a simplex. Thank you. This x we expect to be mirror to this family script x circle. This is called the Batarev mirror construction. When delta is a simplex, it goes back to Green and Plesser. And that's the case we're going to prove our theorem in. And suppose omega is some Kähler form restricted from the ambient toric variety with positive coefficients like this. Then we have some lambda point. Lambda is the Novikov field. I'll write the definition in a sec. We have this point d of lambda in the base of that family, and the bounded derived category of coherent sheaves of that fiber over that point. So this is some, let's say, variety over lambda, is quasi-equivalent to the split-closed derived Fukaya category of X with this Kähler form. Can I say what?
There's two natural Kähler forms in this context. There's one that's the symplectic reduction Kähler form, and then there's the other one that comes from the embedding into P.
A Kähler form is determined up to symplectomorphism by its cohomology class, and I've given its cohomology class here. So. And we have a bit of information about what this point in the base of this family is. Its valuation is equal to lambda. All right, so people may not have seen the definition of lambda before, so let me write that here. So this lambda is the Novikov field, and it has a valuation map that looks like this, that is equal to lambda I for the smallest lambda I such that this coefficient is non-zero. smallest non-zero power of t that appears. So that's that valuation appearing down the bottom. Okay, this is the theorem. Ivan is going to talk about applications of this theorem to symplectic topology. I'm going to talk about the proof of the theorem and how it uses this idea of cutting out a divisor. Any questions about the meaning of the theorem or the statement?
What is the, in the parentheses in the upper or there's a x upper 0, what is that? An equation.
Chi, that's a chi upper 0. So we have a basis of sections of our line bundle corresponding to lattice points inside delta circle. And this is the section corresponding to the point 0, which lies in the interior of our reflexive polytope. All right. Let X be a compact, complex manifold D a simple normal crossings divisor. That means it's not necessarily, it can have multiple components, but they intersect, they're all smooth and they intersect transversely. So a relative Kähler form, oh, bollocks, okay, that's all right, is a Kähler form omega equipped with a Kähler potential on the complement of D, with a certain prescribed form near D. I'm playing with fire, putting my notes close to the abyss there. So X minus D becomes a convex exact symplectic manifold, convex at infinity. That has to do with this prescribed form near D. Now, I want to give you a little picture of what the result I'm going to prove is about. So there's this idea, which is due to Paul Seidel from 2002, which, I mean, I'm kind of paraphrasing, but it basically says, let's look at instead of the space of all califorms, let's look at the space of all relative califorms relative to a divisor D. Then we can compactify it. We can put in some boundary, which corresponds to letting the caliform become infinite along D. In this compactification, somehow the deepest point corresponds to the Fukaya category of X minus D. Symplectic form has just become infinite along all components of the divisor, and this corresponds to the Fukaya category of the complement of D. And the idea is, if we can understand this, try to understand the Fukaya category in a little neighborhood of it using some versality idea. So that's the kind of picture we have in mind. Okay. So if our divisor has components dp, then this relative cohomology group with coefficients in R is just R to the p. And any relative caliform defines a cohomology class in this relative cohomology group. And we're going to define a certain open convex cone inside this space called the ample cone. And it's exactly the cone of effective ample divisors supported on D. So effective means all these lambda p have to be positive. Okay, and a cohomology class, so this is in this relative cohomology group, is represented by a relative caliform if and only if it lies in this ample cone. So that's familiar from the usual Kähler cone. Now let n be some open convex subcone of this ample cone. We're going to define ne of n to be the set of all classes in relative H2, x relative to x minus d, which pair positively with all A inside this N. And we're going to define a ring which is going to be the coefficient ring of our relative Fukaya category, which is the group ring of this monoid completed. There's a unique maximal toric ideal, and we can complete at that ideal. And note there's a homomorphism from this ring to the Novikov field lambda, which is defined up there, sending r to the u to t to the omega of u so long as the cohomology class of omega is inside this cone n. If it's not inside the cone, then when you take this completion here, you're going to end up with certain infinite sums of things here, and when you try to map them over here, they won't converge. Okay, now I'm finally ready to define the relative Fukaya category that appears in my title. So the objects of this category are closed exact Lagrangian branes in the complement of D. Morphism spaces are the free R of n modules spanned by intersection points. The A-infinity structure maps count holomorphic disks mapping into X with boundary on our Lagrangians. and we weight them by an element of our coefficient ring, which is r to the u, where u is the homology class of this disk u. Why does this lie in this ring, R of n? Because everything inside n is an ample divisor, and it's an effective ample divisor. Yes, effective ample divisor. Any effective ample divisor you can kind of perturb a little bit so it's actually a smooth ample divisor near D, and holomorphic disks always intersect ample divisors positively. Even if they have funny things like spheres bubbling off inside the divisor, you're still going to get positive intersection number. Okay. For comparison, the Fukaya category of X has objects closed Lagrangian branes inside X. Morphism spaces have the same generators, but they're linear over the Novikov field. And the A-infinity structure maps count holomorphic disks weighted by T to their symplectic area, which is an element of this Novikov field. So if you look at these, if you compare these two definitions, you see that we have an embedding from the relative Fukaya category into the absolute one by specializing to lambda coefficients via this map from R of n to lambda that I defined up there. Another way of phrasing this is, since this category is defined over R of n, you can think of spec of R of n as this compactified Kähler moduli space that I drew on that board, relative Kähler moduli space. And these maps from R of n to lambda, that corresponds to a lambda point of this moduli space, which in fact lies in, misses the compactification divisor. And this tensoring with lambda is what you call taking the fiber of this family. So we can say the fiber of the relative Fukaya category over this lambda point embeds the usual Fukaya category. Okay.
Depend on the pair XDs, or is it just a complement X minus?
Very much, because we're counting holomorphic disks which map into X, so they go through D. So if you blow something up inside D, you get a different boundary divisor, and the indices of disks will kind of change.
But in what sense you're taking the area of the relative class inside X minus D is going to depend where boundaries apply?
You mean what is T to the omega of U?
Not that, because U is a class in X with boundary in X minus D.
Yes.
But the area of it is going to depend where the boundary is going.
Yes, we're using the fact that omega is...
Down there, where you define down there.
Yes. Yeah, what I defined up there, I should really have said you take symplectic area of the disk minus the chosen primitive for the Kähler. So we have a choice of Kähler potential, which gives a Liouville form for our Kähler form when restricted to X minus D.
Okay, so
And we subtract the evaluation of that primitive evaluated on the boundary of U to get a well-defined thing. Yeah, that was hidden when I said these things. The way you define this cohomology class involves the choice of primitive on the complement of D.
So when you say exactly on example, you consider only exactly with respect to that particular primitive?
That's correct. So in fact, you know, what I would wish to say is that because we see we have this lambda point of this moduli space corresponding to any relative Kähler form, that somehow this family of categories over this guy sees the Fukaya category for all of these different relative Kähler forms. However, of course, if a Lagrangian is closed exact with respect to one relative Kähler form, it's not even going to be Lagrangian with respect to the other ones. So that would be a bit misleading to say that. You should think it's morally true in some sense because as you deform the relative Kähler form, you can follow exact Lagrangians along with the deformation. But all I'm saying is that for this particular Kähler form with respect to which we defined everything, this embedding exists. Okay. So we also have a C point, 0, in spec of this ring, which corresponds to the vertex of this NE of n is some kind of strongly convex cone that has some vertex, and there's a well-defined maximal toric ideal, which we call 0, the corresponding point in here. And that's corresponds to setting r to the u equal to 0 for all u not equal to 0, which corresponds to taking the Fukaya category of the complement of D. Okay. Now, is it 10 past or? Okay. So this fact means this relative Fukaya category is a deformation of this affine Fukaya category over this ring that I've defined.
Does that mean the Hopf spaces are flat?
Yes, they are by definition.
Oh, yeah.
They're free. So, so what do I mean by a deformation? A is a deformation of A naught. A naught is a C linear category over R of n if just on the level of morphism spaces, we just tensor with this ring. But the A infinity structure maps can have higher order terms given by multiples of r to the u, where r to the u are the generators, or the elements, the monomials in this ring R of n. Sorry. Suppose we've got, consider the classes UP in relative H2, which have intersection number 1 with the divisor dp and 0 with all the other ones. So you can think of these as little disks just transverse to that one divisor. So you need to put some minor hypotheses on n, but when you do, the bits of the A infinity structure corresponding to these UP define classes for you in the Hochschild cohomology of A naught. And these are called the first order deformation classes. So how are they defined explicitly? Well, they count holomorphic disks which intersect dp in one interior point and none of the other divisors. So you should compare this with the closed open map from symplectic cohomology to Hochschild cohomology, in case you're familiar with that. Yes?
and x, but for x minus d?
So the Fukaya category of x minus d has the same objects as this. Its Hom spaces are just C linear, and it counts disks mapping into x minus d. So really, it's all defined completely internally to x minus d. Sorry for not mentioning that. We say this deformation is versal if for any other deformation B of the same A naught and having the same first order deformation classes, there exists an automorphism of this coefficient ring R of n and this B, this other deformation, is the pullback of A along this psi star, which basically just means you apply psi star to all of these coefficients in the expansion of the A infinity structure. Okay. Now, actually, I think I'm going to write the main theorem on a big blackboard. So suppose we've got some subcategory of the relative Fukaya category. It's a deformation of A naught, a subcategory of the affine Fukaya category. And let's suppose it satisfies firstly, this open convex cone N has to be nice in a certain sense. So actually all I need is C1 of X is torsion. And in fact, there is a version of the theorem if X is semi-positive, but let me just state the version where X is Calabi-Yau. It's slightly simpler. Okay. Here's a really horrible assumption that we really don't want, and I'll talk about how to remove it next. final assumption is that the closed open map from symplectic cohomology to Hochschild cohomology of this subcategory A0 should be surjective. And the conclusion is that this A is a versal deformation. Now let me make some comments. Firstly, why are we unsurprised this is true? Deformation theory happens inside Hochschild cohomology in degree 2, which by our fourth assumption is the image of symplectic cohomology in degree 2. And under this third assumption, it turns out that this guy is just spanned by the little basic orbits linking the divisors, each component of the divisor. And these correspond under the closed open map to our first order deformation classes. So any deformation that happens in those directions, we can deform away by fiddling with this map psi star. If H2 of x minus d is non-zero, that gives us some extra classes in SH2, which could correspond to classes in HH2, which would be deformations that are not geometric, and our Versality theorem would not hold. One way to get around that is if you have a group action acting on X and D and acting on this subcategory A, then it suffices for the G equivariant part of this H2 to vanish. And a particularly useful case where this really happens a lot of the time is where G is just Z mod 2 and it acts by an anti-holomorphic involution. And this gets rid of a whole bunch of cases. Final note, since we require N to be nice, somehow the result of this theorem only tells us information about the Fukaya category of X equipped with a nice, relative Kähler form whose cohomology class lies in a nice cone. And this is potentially a restriction on the applicability of this theorem. But if X is sitting inside a toric variety, and our divisor is the toric boundary divisor, then any Kähler form which is restricted from the ambient toric variety sits inside a nice cone. And there could potentially be other relative Kähler forms on X relative to D, and I don't know how to check that they lie in a nice cone. So the applicability is somehow restricted to ambient toric Kähler forms. All right. I'm just about out of time. So how do we actually apply this? Very briefly, to prove homological mirror symmetry, we look for some B in perfect complexes over this mirror family script X circle that I defined way back at the start. We want to match up a subcategory of the relative Fukaya category at 0 with this subcategory B. Then we need to check the first order deformation classes match. Then that means by this Versality theorem, well, we need to check its hypotheses, but it means we automatically get to match up A with the pullback of B by some psi, which we call the mirror map. And at this stage, we can embed this thing in the absolute Fukaya category, embed this thing in the category of coherent sheaves over some lambda variety, and we have these automatic split generation results that mean it automatically upgrades to an quasi-equivalence of the whole Fukaya category with the whole bounded derived category of coherent sheaves. Finally, if we want to determine psi, we can use the relationship between homological mirror symmetry and Hodge theoretic mirror symmetry to determine this psi uniquely, and this allows us to determine what the mirror map is, what the precise corresponding variety is. I think I'm out of time. I'll stop there. Thank you.